Hello everybody, my name is Gajecki and I'm a PhD student at the Hanover Medical School, working with the auditory prosthetic group. And today I would like to present our submission for the ICASSP 2022, entitled An End-to-End Deep Learning Speech Coding and Denoising Strategy for Cochlear Implants. So first I would like to introduce the concept of cochlear implant, or CI for short. A CI is a surgically implanted medical device that can restore hearing to a profoundly deaf person. The sound is captured by a microphone and transduced to stimulate the auditory nerve electrically. We can see a depiction of such a system in the figure on the right of the slide. It consists of a speech or sound processor, here marked in red, behind the ear of the subject. And this piece is the one that contains a microphone that captures the sound and all the necessary DSP to process the sound. Once that's done, it's sent to an emitting coil located in the head of the subject through a magnetic field. I will send the information through RF frequency through the skin and received by a receiving coil, or the implanted body at the other side of the skin. The receiving coil will decode the signal and send it through a cable to an electrode array inserted inside the cochlea to stimulate the auditory nerve. In this work, we will focus on this part here, what happens in the speech or sound processor. The algorithm used to transduce the captured audio signal to the electrical pulses is called the sound coding strategy. In this work, we will focus mainly on one specific sound coding strategy called Advanced Combination Encoder, or ACE for short. This is one of the multiple or different speech sound coding strategies used in different CI systems. We can see a block diagram of the ACE sound coding strategy. So in this case, once the audio is digitalized by the speech processor, it's sent to an FFT, which will convert the time domain signal into a 65-bin spectral representation. Then it will be sent to an envelope detection block that will group these 65 frequency bins into 22 bands. Then, out of these 22 bands, n spectral maxima will be selected, which will be then compressed through a loudness growth function, or LGF for short. These values will be compressed between 0 and 1 specifically. And finally, the mapping block will map these values between 0 and 1 between the C and T levels of the subject or electrode and for each electrode. The T level is or threshold level is the minimum amount of current needed to elicit the sensation of hearing, and the C or comfortable level is the amount of current needed to elicit a comfortably loud sound at a given electrode. Finally, here at the end of the block diagram, we can see a visual representation that we use to monitor how the auditory nerve is being stimulated in time. This is what we call an electrodogram, and resembles a spectrogram in the sense that we have the time domain in the x-axis and the electrode being stimulated in the y-axis, which is kind of a frequency representation. In this work, we will focus mainly on using 8 of the 22 available electrodes. So we will select 8 maxima in the band selection block that I mentioned before in ACE, as shown here in this figure. Regarding the current CI technology, CIs provide open-set speech understanding in the majority of patients, including the use of the telephone. Children can achieve a near-to-normal speech and language development if implanted early enough. These benefits are greatly reduced, however, with background noise. And front-end speech enhancement algorithms can be used to remove interfering background noise, which is the main motivation of this work, is to develop a speech sound coding strategy that performs speech denoising to allow CI users to understand speech and noise conditions. So these are two of the baseline algorithms that we use in terms of speech enhancement. The first one is a classic Wiener filter, which estimates a mask to remove the background noise. And we can see it in the first block diagram. In blue would be the pre-processing part, where the Wiener filter is applied to extract the target speech, and then is sent to the ACE sound coding strategy. The second approach is a more state-of-the-art, and it's based on deep learning and audio end-to-end speech enhancement. In this case, we use the TasNet. And as we can see in the block diagram below, this performs audio end-to-end speech enhancement, so it estimates X hat, which is the target signal in the audio domain, and this is then sent to the sound coding strategy to obtain the desired electrodegram. So this is our approach, which we call deep ACE. And our approach is meant to do two things. One of them is to code the signal, such as ACE sound coding strategy would do, and the other one is to also perform speech denoising when background noise is present as well. We can see a block diagram of our approach here, and we can see that it captures the raw audio signal and it will estimate the output of the LGF to be sent to a band selection and mapping block. So if we compare ACE to deep ACE, we can see there are some similarities. So basically we substitute most of the block diagrams except the band selection and mapping block. And the reason for that is because these two blocks are subject dependent. So the band selection doesn't necessarily have to be 8 out of 22, but it can be any different number. And the mapping is also highly subject dependent because the TNC levels will differ between them. So in terms of regarding the topology of the separator we use for both the TasNet and the deep ACE, it has to do with 1D depth-wise dilated temporal convolutions, or TCNs. And the hyperparameters used for both the front end and TasNet and the deep ACE are shown in this table here, if the listener is interested in them. To train the models, we used two datasets. The first one was extracted from the Clarity Challenge, and it consists of 6,000 sentences and noise between -6 dB and 6 dB SNR, and it includes 24 different speakers. As a validation set, we use also the validation set of the Clarity Challenge, which consists of 2,500 sentences and noise, including 10 different speakers. We use this set to monitor the model's training performance. We included also an extra dataset, the dataset number 2, which is based on German speaking sentences, which we mixed in CCATT, speech-shaped noise, and ICASSP 7, modulated noise. We used 30% of this dataset, and we included it in the training set, and this remaining 70% we used it for final evaluation, using objective instrumental measures and speech listening tests. A difference between the front-end TasNet training and the deep ACE training had to do with the loss function use, and that had to do with the nature of the output of each of the algorithms. Because the front-end TasNet was performing audio end-to-end speech enhancement, we use the scale invariant SNR between the target and estimated signals. And for the deep ACE, because we are estimating the output of the LGF, we basically minimize the distance between the target clean speech and the estimated speech through a loss function called mean square error. Here I will show some examples of the output electrodegrams of each of the algorithms. This will be the unprocessed clean speech by ACE. This will be noisy signal, noisy speech processed by ACE. This will be the output obtained if we use the Wiener filter as a front-end processing block. This is what we obtain by using a TasNet as a speech enhancement algorithm in the front end of ACE. And finally, this is our approach, deep ACE. We can see that the last two deep learning methods are quite successful at removing the noise in the background. If we compare it to the actual clean ACE, we can see the similarities between the obtained estimated clean speech and the actual clean speech. To quantify the actual performance of the different approaches, we used a couple of objective instrumental measures. This is the first one, and it's called, this is the SNR improvement that characterizes the amount of removed background noise. In this box plot here, we can see the SNR improvement as a function of the input SNR, which ranges between -5 and 5. And on the y-axis, we have the actual SNR improvement. In this case, we tested it for the CCITT, background noise. And we can see that all the algorithms obtain in general a mean SNR improvement. This is what we obtain when we mix this speech with ICRA modulated noise. we can see that TasNet and dpace are consistent or robust in terms of different noises, but Wiener here fails to give a substantial benefit with respect to the unprocessed signal. As a second objective instrumental measure, we use the short time objective intelligibility score, also for 3 different input SNRs from -5 to 5 dB. And in this box plot, we show again for the CCITT the STOI obtained for the unprocessed ACE, for the Wiener plus ACE, the TasNet plus ACE, and the dpace. And we can see again that both deep learning approaches are the ones with the highest means in general. And this is what we obtain for the ICRA, with the ICRA background noise. And again, we can see that Wiener fails to improve with respect to ACE when compared to TasNet and dpace. And regarding the speech results, first we tested speech in quiet to assess whether the front-end TasNet plus ACE and dpace were compromised in terms of speech understanding in quiet. If there's some artifacts or things like that that could cause a problem in terms of speech coding or sound coding in general. And we can see in this bar plot, we can see the individual results for each of the 5 subjects tested. We tested them with direct stimulation, by the way, using a research interface. And we can see in the y-axis the percentage of correct words understood for each of the subjects, and the last 3 bars represent the mean. And we can see that the relative differences between the approaches are there are almost no difference, basically. So we can conclude that the sound is transmitted, at least in terms of speech understanding, the same way as ACE would. And in terms of speech and noise, we also tested these same subjects with background noise, specifically ICRA sound noise. And we assessed the differences between unprocessed ACE and the 3 investigated approaches, that is the Wiener, TasNet, and our approach, the dpace. And again, if we go directly to the mean, we can see that, again, TasNet and dpace obtain substantial benefits in terms of speech understanding, at least in this group of people. And this benefit is around 40% more percentage of understood words with respect to unprocessed ACE. So to conclude, in this work we propose a speech coding and denoising strategy for CIs, and we didn't observe any speech understanding differences in quiet when compared to ACE when using dpace or the front-end TasNet. In the context of speech enhancement, dpace shows slightly worse performance than the front-end TasNet approach, but this may be potentially due to suboptimal cost function used. This should be further investigated. Speech perception scores obtained with dpace and the front-end TasNet were very similar. However, dpace reduced the algorithmic latency with respect to the front-end TasNet by 2 milliseconds. And we think that the proposed method has the potential to completely replace any CI sound coding strategy, while keeping its general use for every listener in performing speech enhancement in noisy conditions. So thank you very much for your attention, and looking forward for questions and potential discussions.